And now, I just want to say that I'm very happy about this talk because I don't know if you realize that, but we only had one keynote made for an Argentine. That was Maximo in 2007, and then I don't know why we never realized that all the keynotes were from people outside of Argentina. And, okay, so now this is the second keynote from an Argentinian, and I think it's great stuff that we're doing that. So,
okay, thank you. So what I don't know what a keynote is, but it's sort of longer talk about crazy things that you have been thinking. So, well, the title is a small talk expression that tries to convey the idea of how do we find the next idea, right? So a stream is something that essentially gives us more objects, the next object. So this is a small talk expression, and what we want to think about today, I want to think about today with you guys, is how do I find the next idea? And there are many connections with the keynote we had today by Kathleen, because education is something that worries everybody. And so I wanted I started thinking in this sort of meta idea, so ideas on how to have new ideas. And of course, the first thing was something that we already heard this morning, is that if we think the conventional approach of education is that we first teach something or are taught something, then we ask questions to check that the information or knowledge has been acquired, and then we repeat. This cycle is basically the traditional approach to education. And where we as teachers spend most of our time and energy? Well, in motivation, right? We make the most of ourselves to try to motivate the students. That's like the key in this model. The second place where we put a lot of attention is in selection. What are the questions or the problems we are going to propose to check that the knowledge has been acquired? And then we repeat the cycle. And when we repeat the cycle, the third concern appears, which is pace. So how long we will stay in one subject, and then we will move to the next one. So we as teachers spend all our energy and time in motivation, selection, and pace. Okay? These are our main concerns in the traditional approach. Now, if we go and think in the way we learn things, is usually we start from a question. There is something that interests us and we want to solve or understand. So, and then we go and learn something in order to solve that problem or question. And then what happens is that we motivate ourselves, because let's assume that the question is our question, not the question to pass an exam or something like that. And so the selection comes here, in what we learn in order to answer the question. Okay? So the problem is, in this model, is why would I have a question? Okay? How I get a new question. And of course, then we repeat, and if we have a mechanism, a method, let's call it a method, to fill the item number one, then we would be in a virtuous cycle where we ask the next question, we are interested in answer, then we select something to learn, we learn, and keep going. So this is more or less the difference between being taught and learned. Okay? So So in this model, I really don't need a new idea or ideas on how to have new ideas. I rather need ideas in how to make new questions, because we have somehow to create those questions, but questions that we ourselves create. And the problem I see, and I've seen at the at least at the tertiary level at the university, is that we teach students how to solve problems, but not how to come up with their own problems. We are not teaching how to create new problems for every individual so that they can create problems. By the time someone starts creating their problems, they are doing research. But this is something that we don't teach until, I don't know, the PhD phase or something like that, very late in the process. We don't teach that from, I don't know, lesson 1. It's not systematic. What is systematic is the problem is given, okay? So I will emphasize about questions rather than ideas. So I have a theorem. It's not actually a mathematical theorem, but looks like a theorem. And the theorem is that great thinkers have a method for finding new questions. It's not that they just have new questions because they are super smart. They might be very smart, but they have a method they follow. And this method triggers the next question. So I will change the title of this talk, changing ideas with questions. So it's self-questions as stream next. How do I find the next question? The ideas will come eventually, okay? So let's think in small talk. So I would like to implement this class, the question stream, okay? And I'm talking about my theorem, so I want a method to implement the main message of this class, which is next. And of course, I don't know how to do that, but this talk is about insights on how to implement this method. So next would be something like do this, do that, and answer the next question. But now, think of this class. There is one method that all of us know how to implement. Think for a second. The question stream, what is the method that we all know how to attend? Exactly. So at N, we know how to implement this. Okay? Now, look, but think, just by creating the name of the class, we are creating the concept, so we have our focus there, and there is a sort of satisfaction when we discover how to implement this method, which is trivial, but has a lot of meaning. Okay? So, the idea is to review the history. So let's go back some few years. Let's say 2,600 years ago. So, because something that bothers me is that we are like crazy trying to be updated with every new technology, and what are we going to do with the world that is changing, and I'm not familiar with everything, and I don't know all that I should. What are my kids going to do? Okay, but let's go for a moment and review the thinkers, at least from the viewpoint of my theorem. Okay? So I picked someone. So this morning I was trying to practice how to pronounce this in English. It's something like Thales of Miletus. Okay? This was a mathematician in minus 16. So it's Tales de Miletus in Spanish or other languages. So this guy was working in geometry. So his method was about abstraction, and a very precise form of abstraction, because at that age they had many examples of, for instance, triangular shapes. Okay, so these guys that I represented with this Thales of Miletus had this method. They abstracted the shapes and draw the shapes not on paper but on some wax slate or like the tablets of those times, or sand slates or something like that, and start doing very precise drawings. So already at this time there was a lot of knowledge about geometry. For instance, they knew that if you sum the internal angles of every triangle, then the sum is 180 degrees, with the definition that 180 is this angle, the no angle thing. Okay, and so how do they knew this? Because this is the way these guys thought, because they replaces reality with this abstraction. So in this abstraction you start drawing lines. Okay, so if you draw a parallel to the pink line here, you immediately see that the green angles are the same. Okay, and for the same reason you see that the red angles are the same. So it's very clear that green plus white plus red is the no angle, 180. So this is knowledge. Okay, so the interior angles of any triangle always sum 180. So they knew these sort of things. So Thales was a little bit further and started to think about special triangles, and also the circle played a central role in all these theories, because they have the pair of compasses and they have rulers, and so this is the technology was very suitable for these drawings. So this is a theorem by Thales. What he says is that if the pink side is a diameter, so hits the center, then the third angle is right. It's always 90 degrees. Always. No matter where you put it. And so this is not just drawing. This is more on measuring things. Okay? So, and why is that? Well, if you draw here a radius, and so you have this triangle, okay? But this triangle has there are two sides that are equal to the radius, okay? So it's an isosceles, so these two angles are the same. And if you repeat here, because of the same reason, in this triangle, these two angles are the same, because the triangle has two sides that are equal. So now, from the previous theorem, we know that green plus red is 180, because it's a triangle. And so you know that green plus red is 90. So these guys were not just finding relationships. They were defining understanding. What is understanding? Understanding is not remembering the formula. It's actually being able to see why it works. Okay? So this is 90. So approximately 100 years later, we have Pythagoras. Okay? And Pythagoras has his famous theorem. We will talk a lot about this theorem later, but let's picture it as a squared plus b squared equals c squared. And now Pythagoras goes a little bit further. Let's stop here. Because he's now using metrics to deduce new distances. Okay? You can think of this as more practical knowledge, because you can measure things, and you can also use the theorem to know whether or not an angle is a right angle, which is important for practical reasons. But these guys, Pythagoras in particular, were not thinking in applications. They were already so embedded in these abstractions that they didn't care anything about the practical and real world. They enjoy being there, like we enjoy being in the cloud. They enjoy being in this cloud of geometrical objects with pictures and other kind of tablets. So it's the same thing. It's the same thing happened many, many years ago, thousands of years ago. 100 years later, we had Aristotle. This guy was thinking, because by this time, they had a lot of knowledge already. So, and theorems and many, many things. Knowledge with that meaning, the meaning of understanding. Understanding very clearly, okay? Not knowledge like information. So this guy started to think, how are we reasoning? So thinking about thinking, or reasoning about reasoning. So the logic was invented here, was studied very carefully. It's like the invention of if, or if-then, okay? So if or if-then were invented here. Then we have Euclid, and now, 100 years later, we have an incredible advance. We have axioms. What does it mean? That by the time of 300 BC, the amount of knowledge in geometry and mathematics in general was so vast that this guy, Euclid, thought, okay, could we reduce all this knowledge to a minimal expression? The idea of having like a universal law or something like that, like in other sciences, modern sciences we want to have today. So axioms, so the guy did this. He reduced all the knowledge from centuries ago at that time into 5 axioms. And the axioms are very simple, like this. If you have 2 points, then there is one straight line across the 2 points. If you have a segment, you can keep going through the segment and you will have a line like in axiom number 1. Number 3 is to describe a circle, you only need a distance on a point. Number 4 was all right angles are equal. And the 5 was much more elaborated. And he didn't want to add that axiom. The actual axiom is like, if you have one line and 2 lines crossing that line, you have 2 sides, okay? In one side, if you sum the angles that the lines crossing the division, you sum them and you obtain more than 180, okay, that is the bad side. And so the other side, you have less than 180, so the 2 lines will meet in that good side. Okay? Much more elaborated than 2 right angles are the same, okay? So he tried to avoid that axiom and couldn't. So he was forced to introduce that. But then, with these 5 axioms, he could rebuild all the knowledge of the geometry known until his days, which was incredible prolific work. Because he could reduce everything to these 5 axioms, and from these 5 axioms, prove all of the others as theorems following Aristotle's logic. Okay? This is exactly what happened with Smalltalk. Smalltalk came with, we could say, two axioms, object and message send. And these guys that invented Smalltalk recreating all the knowledge in computer science from these two axioms. They rebuilt the whole thing, everything, processes, collection, data structures, iterations, whatever, everything, file system, everything from these two actions. It's the same. So this is like, again, this is a method, okay? So in the case of Thales, we had the method of abstraction and drawing lines and finding relationships. Pythagoras goes a little bit further and uses the same method and gets more profound results. And then we have Aristotle that thinks about reasoning just to make sure that by the day we need a rigorous deduction or theorem, we won't fool ourselves. And then Euclid, using that, invents his own method, which is let's deduce everything from the actions. Okay? This is very prolific idea. So for Euclid, the method next in question stream was solved. Okay? And then we had 100 years later, Diophantus. Diophantus basically invented algebra. And one thing, one of the reasons I chose him is because he wrote a lot. And his books were lasted for centuries. So he wrote, of course, about all the things we have been mentioning, especially about Pythagoras and all those things. So now we skip many, many years from 200 to 1600. So this is Fermat, okay? Fermat became popular in the, 20 years ago or something like that, but was very popular among mathematicians because he had this thing. He said, in 1637, he said, there is no way to express the sum of two powers as another power, if the power is greater than 2. And why Fermat made this claim? Because he was reading Diophantus. Fermat, think of this, Fermat was the greatest mathematician of his time. Was the best. He was the best. He invented a lot of things. For instance, many of the cryptography algorithms, the good ones, come from theorems by Fermat. And many, many other things. But the guy was reading a book that was, 1,400 years old. So he was not too worried about what was happening in these days. He was, maybe, but not only on that. He was also spending time reading something that was very ancient. And what happened was that he was reading about the Pythagoras theorem, which is a square. So is the case when n is 2 here. So the next question was, what is if instead 2 I put n? Okay? So his method was, we could say, or at least one of his methods, let's go to the sources, let's go to the origins, let's read the classics, okay? And let's review, because of course he knew perfectly well Pythagoras theorem. He was re-exercising, he was reinventing the wheel. Don't reinvent the wheel, that's, I don't agree with that. Reinvent the wheel, it's a lot of fun. And so what happened with this theorem is that became very famous. Fermat died, and nobody could find a proof for the theorem. There were many, many theorems by Fermat, and so the mathematicians were reviewing all the theorems. So some had proof, some others didn't, so they wrote proof here, proof, so everything was checked. We have a mathematical proof for everything, but that one was nobody could. So new theories were created to solve this problem or disprove it, until in 1995 Andrew Wiles, that guy, could solve the problem with extremely sophisticated mathematics of that time. What he did is there was another conjecture, not the Fermat one, another one from 1950-something by two Japanese guys, mathematicians, that was considered impossible because few people could understand the statement. This is the opposite to the Fermat theorem, where everybody can understand the statement. So it was a relationship between two theories that had nothing in common, were so distant one from the other that nobody in the world knew both theories. So they couldn't solve nobody could solve that. But by the time when Andrew Wiles was thinking about this, there were some ideas that maybe that conjecture, the one I'm referring to without explicitly announcing it, could have this simple problem as a consequence. So the guy went and solved the very hard one, and he succeeded. So as a corollary of that, he proved the theorem. So in the case of Andrew Wiles, his method is, let's choose a very well-known and very hard problem. Let's take an old problem that many people have tried to solve. Let's study whatever it takes. Let's do whatever it takes, and until we can make a contribution and probably solve the problem. And he did. Okay? And there is something else about Andrew Wiles, his passion. Okay? There is a video where he tells when he could solve the last step in this very large proof, and in the video the guy ends up crying because he remembers the emotion of the moment. So passion and mathematics, passion and science, or computer science, or whatever, is inherently there. It's not something we add or we don't know. It's there. So we have the people that make abstractions, the people that reveal everything from axioms, the people that try to solve very ancient problems, the people that write, they think by writing. And, but all of this is about geniuses. Okay, what about me? Where do I start? And I don't know, but maybe try to understand something. Just try to understand something. This is the approach. This is the approach. When I was working for my PhD, my advisor came one day and started to write some math on the whiteboard. It was a green board. And I asked him what was those things about. And he said, I'm trying to understand something. And that sentence for me had a lot of meaning, because this is the approach. Try to understand something. Statement, thank you. So, but what is understanding? Understanding is not knowing formulas or, Googling for information, or is really being able to see very clearly why something is the way it is. Okay? So, for instance, we said before is 180 degrees or 90 degrees. We have the time notation where this is it's hexadecimal or notation of things that are based in the number 16. Okay? Why is that? If I look at my hands, I think that I can count 10 things, 10 objects, because I have 10 fingers. Okay? But if I look to my hand more closely, I maybe perceive a difference. These 4 fingers have 3 parts, and this one has only 2. Okay? It's like not a real finger, but has a good property that can oppose the others. So maybe I can count like this. 1, 2, 3, 4, 5, 6, etc. until 12, because it's 3 times 4, so it's 12. And then I can say, okay, 12 once. Then again 12 twice, 24, etc. until we hit 60. So I can use my hands to count not until 10 but until 60. And that's why we have so many things that are measured in 60s or multiples of 60 or those sort of things. Another example. Our intuition says that heavy things fall faster than non-heavy ones. This is false, is scientific knowledge. Okay? So you can go and learn that. And maybe you can use Newton equations to prove that. But you are not actually seeing why a heavy thing falls at the same time as a light one. Now, think of this experiment. Think of a ball of 1,000 kilograms and another one of 1 kilogram. So if your hypothesis is that the heavy one will fall faster, then you should conclude that if we connect both, the whole thing should fall even faster because it's heavier. Okay? But if on the other side of the reasoning, the 1 kilogram ball should fall slower because it's not that heavy. So when we connect, it will stop the big one because the small will want to fall slower than the big one. So the whole thing should fall slower. But in the first reasoning, we concluded that it was the other way around. So there's a contradiction. So the 3 things fall at the same time. So you can see this. So more examples of things that we can see. For instance, another basic result of triangles is how do I compute the area of the triangle. So we know it's base times height over 2. And why is that? Well, again, let's use the Thales method of drawing lines, and this is the height, and you repeat this line here and have a rectangle here, so you know that the area of this rectangle is B1 times H, but you divide this into triangles that are equal, because if you rotate one, you get the other one. And so these 2 triangles have the same area, and you repeat the same here with the green triangles. So what you get is that the sum of all triangles here, 2 red plus 2 green, is the area of the rectangle, and which is by B1 plus B2 times H, and then if you divide by 2, you get this. So this is why we can see that the area of the rectangle is what it is. Now, let's use here this information, and let's think of this. Let's compose the Pythagoras triangle of ABC with a right angle. Okay? And let's compose this like repeating the same pattern. Then we are left with a central square. So the question could be, what's the area of that central square? If you start drawing things, many of these questions come up very, very easily. So we know, okay, the area is C squared, because all the sides have that measure, that length of C. But I would like to express C in terms of A and B, which is the Pythagoras theorem. So a way to look at this is you repeat the drawing. There is a trick because there is a small rotation. You see here is equivalent but not the same. And now, because we already know that the area of the triangle is A times B over 2, and all these triangles are the same, now we know something. We know that A plus B, which is the side of the big square, is the same as the sum of all the components, the 4 triangles and the square. So we write that equation. So A plus 4 times the area of the triangle is equal to the big size to the power of 2. Then we expand the right side of the equation. We get this. Then we simplify here and here, and we get this. Okay? So we get that A is A squared plus B squared, and also that A is C squared. So this is a proof of Pythagoras' theorem. The problem with this proof is that you have to follow the steps. You have to know how to decompose A plus B squared and then simplify. So there are intermediate steps that hidden the reason why A squared plus B squared is C squared. So here is another proof that hides much less. So think again on the same configuration, but now let's concentrate in 2 squares. The squares with side A and the square with side B. So I would like to see, not to prove doing calculations, to see that the sum of both squares is the area of the pink square. Okay? So concentrate on those things. So think that you have scissors and you cut and paste things. Okay? So I will cut here. Okay? So you cut here, and then you cut here. And then you move this part here. Okay? So I forget this because I moved there. And then I do the same here. And I get the result. Now you can see why A squared plus B squared is C squared. So the first thing we had to, the just in case part of this, let's insist on ways of teaching what does it mean to see something very clearly. What does it mean to understand something? Okay. Now, you have the Pythagoras theorem. So if Fermat made a lot of notes from that theorem and found some fruitful ideas, why we cannot do something similar at a different scale? So this one thing that you can think of as an exercise for programming is okay, how do I produce? Because, for instance, one example of Fermat theorem is 3 squared plus 4 squared equals 5 squared. So 3, 4, 5 fit very well in the ABC variables. Okay, is an example. And so, how do I get more examples of these Pythagorean triads? Okay, I would like to write a program to produce them all. So it's like asStream. Give me the next triad. Okay? So there is a method, there are many methods, but this one is very, you can see it. It's from a guy called Dickinson, and he invented this in 1920. And so let's see if we can really see something. So you start with a square of side K. And then you pick one sub-square, the yellow one, below. Okay? I'm referring to this. Okay? So now I divide this yellow part into 2 rectangles here. So the area doesn't change because I took 2 parts and split them and put it there. But in order to do that, I need to know that I can actually divide this q squared in two equal parts, and the parts are p times k minus q. You see? This part. So assume that we have the property with the numbers. Then, once I have this, what I get is a new square. Now the side is k plus p. So we have the total area here is k plus p squared, but is on the others also is also k squared plus what is missing here, which is again a square. So you have a square that is the sum of two square quantities. So essentially you have again the Pythagorean theorem. So these are the formulas. So you can use this reasoning to write a class that will produce the next triad with ABC meeting the Pythagorean theorem. Don't bother about the details. What I wanted to show here is that this is a very simple method. You can write in few lines of code. So I wrote it. So I created the list of until, I don't know, some of them. So just by looking at the list, you immediately see that, for instance, this one should be repeated because if 9, 40, and 41 are Pythagorean, then the reverse, 40, 9, and 41 also, because A and B, you can interchange them. So you can now refine your method not to avoid the production of repetitions, okay? Another thing you can, I don't know, maybe you can think of like this one. This is another example where we have 24, 25, like we had 40, 41, and here we have 8, 40, and 8, 41. So the difference between the two bigger ones is just one, okay? So another problem, write a method that finds all the triads that have this property, the two bigger ones differing one. And you can keep coming with new questions. And if you use Smalltalk, it's very easy to have this focus and to have this desire of doing more while you program. So a dialogue between you and your Smalltalk happens, and new questions come, and the cycle of learning repeats. Many more things from the Pythagorean theorems, like what if I put 1 plus 1? Well, I get again, this is 1 squared, so this is again Pythagorean theorem. So C is square root of 2, which we all know is not rational. Again, go and learn why. And for Pythagoras, this was irrational numbers. This is totally irrational. I mean, it was like a big thing to discover this thing, and they didn't tell anybody about this because it was a very secret knowledge. And what can you do? Because in the computer you cannot represent irrational number with all the decimals. Still, you can do some things, like consider, for instance, another subclass of numbers that is like sort of complex numbers, but instead of I, you put square root of 2, but as a symbol, not as the representation with decimals, as the precise quantity. And then you put two coordinates, integer coordinates, and you can do a lot of things in this new thing, which you solve the first equation with infinite precision, okay? So here is how you can represent in a computer a quantity that has infinite decimals with infinite precision. And you can do a lot of math with that. And you can program that class, an extension of the integers that is very interesting. You can think of this as, okay, square root of 2 is a solution of the polynomial x squared minus 2 equals 0. So here, for instance, another idea that you can find is, okay, what if I change the polynomial and instead of minus I put plus, or instead of 2 I put 3 or whatever. And that will, if you keep going, you will end up with very modern and important theories about, I don't know, Galois theory, number theories, algebraic numbers, cryptography, and probably ending up with Andrews Weil proof of the Pythagorean theorem, because all these fields are related to that resolution. What I mean is that you can trigger increasingly more interesting questions. You can find more interesting questions if you try to start by trying to understand something that was well known from thousands of years ago, but you look at them again with fresh eyes using Smalltalk. And that is a method. That is a method for finding the next question. So, how is my time?
10 minutes more.
10 minutes. Okay. I will skip one part by doing it actually, but let's see if it works in our mind. It's not the same, because if you have the Smalltalk there, everything changes. The reality changes. Now, think, for instance, that you want to implement the class triangle. Okay? So you go and create a subclass of object, and you name it triangle. Okay? Then you think, for instance, in the instance variables. So you put 3 instance variables, A, B, C, doing an unusual thing, which is naming them in capital letters, because these are the points, A, B, C, because the triangle lives in some place. Okay. Now, once you have the class, you want to have some instance. So the instance creation method is providing 3 points, one for A, another for B, another for C. You do that. That's okay. But now, Smalltalk engages us, and you all have lived this feeling, that you want to put another method there. So, for instance, what if instead of having the 3 points, I have the 3 lengths? Or, so you do that. Or harder, what method can I, so this is on the instance creation. What sort of question may I ask to this object? For instance, the easiest one, if you have a triangle, the easiest question you can make to a triangle is the perimeter. Okay? This is very easy. You sum 3 numbers. The perimeter. The next one would be the area. But the area, we saw, you need the height. And the height is not so easy to compute. So what you can do there? So you can think and use trigonometry or those sorts of things, or Pythagoras, and start, or you can go and Google triangle, or go to the Wikipedia. I went to the Wikipedia, triangle. There's all sorts of properties about triangle, or beautiful ideas for my class. And there is one that reads, the area is a very simple formula with the semi-perimeter. So the perimeter divided by 2 is something like, I don't remember, but the semi-perimeter, let's call it S, is like S times S minus A times S. I mean, very simple formula. So you implement the area, and then for free you get the height, because the area and the height are related, and you keep going. So it's very compelling to enrich your class. So it's a method we have to get the next question. And then we select, for instance, from the Wikipedia, the next piece of information we want to learn. But we go back and exercise those learnings and, I don't know, create instances and start sending messages to them, and new questions will come. We all know that. So we have the method. But now I want to go to the what happened in the art, because before we were reviewing the science, okay? Let's review the art, because there are great thinkers in the arts. Do they also have a method for thinking new ideas, for finding new questions? Or is just that they have inspiration out of nothing and come and paint something or play some music? So I choose 3 examples. The first one is Richard Wagner. And this guy, what he did, his method for create, his field was like operas. He didn't call them operas, were dramas, musical dramas. So a musical drama is a very long poem, so the lyrics, the music, and the characters, the scenic representation. So the method for Wagner was, okay, I will decompose everything that is in my drama into small parts. So for instance, I will have characters, this guy, that guy, that have names like Siegfried or Sigmund or many, many others. And I also have objects like swords or trees or fire. And also I will have feelings like love, hate, fear, whatever. So for every of these, every single entity, he wrote a piece of music. He called a leitmotif. It's not a melody, it's less than a melody, it's shorter, it's a phrase. But it's a phrase that is one of the attributes of the object. So the object can be a person, can be a god, can be a thing, like a ring, or a sword, as I said, a tree, etc., a river, a fire, or it can be a feeling, love, etc. And for them, for this guy, all of these entities were objects. They have name, behavior, and a leitmotif. And here are some examples. This is the Siegfried, one of the heroes of the drama, of the many dramas he wrote. And so let's see if I can show you this. No, not connected. No, it's not that important. But the thing is that all of them are this short. Okay? Now, the problem with this method is how do I create all the music and all the circumstances that happen in the drama? Is only by combining the thing. There is no such thing as the theme A and the theme B or something like that. It's only leitmotifs. And the leitmotifs enter when the thing enters into the stage. You see, so if you have character A and character B having a fight or a discussion or whatever, or a dispute, then you will be hearing the music of those characters, and if there is a feeling, the leitmotif of that feeling appears, and so in that way he composes everything. It's object-oriented music. In the purest way of the meaning. It's not similar, it's the same, exactly the same. Picasso. What was the problem that Picasso wanted to solve? Well, by the time Picasso was working in painting, painting was extremely developed over many centuries. So they had developed for instance, this perspective was very well known. And so the problem was, okay, perspective is perfect. It's already perfect. So I have nothing to do with painting. It's already perfect. I cannot add anything. So I will find a problem with this. And the problem is, okay, perspective is only one viewpoint. Alan Kay says another viewpoint is worth 80 IQs or something like that. Okay? But, Picasso did it first. And so he found the problem. So let's solve the problem. So the problem is, let's forget about perspective. How I represent 3D objects or several viewpoints in one thing that is 2D because it's the canvas. So she didn't care. She just created cubism. In cubism, the idea is to overlap all the viewpoints into the same canvas. And so there is a rupture with perspective, but he added another ingredient, is instead of being as detailed as possible, like in traditional painting, let's put as few details as possible. This is incredibly powerful. So he created beautiful things like this. These are two women reading. So you can see the two aspects. The multiple viewpoints overlapping and in the same plane, and the economy of details. Okay? The economy of detail. And it's still art. It's very interesting. It's new. He solved the problem. His method worked. And here is another example. These are musicians playing their instruments. Same idea. So, in the traditional approach, meaning, and this morning we had this excellent talk by Kathleen about meaning, learning meaning. Meaning, in the traditional approach, came from perfection, detailed reproduction, okay? And here, in Cubism, meaning comes from suggestion, evocation. I will give you the less possible, so I create this tension where you find the meaning because you have been suggested something. So it's not only multiple viewpoints, it's multiple meanings at the same time. So viewpoint in a broader sense. And the last one, there are many, but sometimes you have to stop. So Antonio Gaudí, the Spanish architect. We had a wonderful ISAC conference years ago in Barcelona. So we went to the house, this house, the Batlló house that he built. And the idea here is Barcelona is on the seaside, okay? So on the beach, it's close to the ocean. So he took this metaphor of the ocean and built a house with several stories, but following the metaphor of the ocean. But not just trying to make a mimic or imitation, reproduction of the ocean. It's just a way of, it's an inspiring thing. Let's create our own ocean. So there are all sorts of curves in the architecture, and the columns have plants or animals or things that go from one nature or biology to the other, and the windows, the balconies, everything. But there is everywhere a uniform metaphor. The uniform metaphor of the ocean, of being immersed in the water. And this happens not only with the shapes or the curves or the decorations. It also happens more profoundly with flows. So there is a flow of light, of natural light that Gaudí enforces by using different shades of blue in the tiles and in the painting in the building. So if you go to the top of the building, there is clarity because you can see the light from the sun in the surface. And if you go deep, the blue gets more intense, and there is more mystery. And so there is light going through flows that are very clearly designed, and also there is air, because it's a warm city, Barcelona. So air was very important, so there is flow of air. So it's not just the many windows, it's also the interior windows have mobile parts that let the air go through, and also for the people to go from one place to the other. It's like three flows of light, air, and people, the creatures of the house, that can flow, and everything follows the same metaphor. So, see, if you want to follow one metaphor, you cannot go to I don't know, to the supermarket and buy, I don't know, a door, no? How do you call the manija de la puerta? No. The door knob, or you cannot go and buy a chair because won't fit there. So he built everything. He built the tiles. He built all the decoration and all the parts. And also he was an architect, so he built the infrastructure of the house, because it's a big house. And the infrastructure, he exposed the infrastructure. So elegance was a component, because if there is no elegance in the infrastructure, there can't be any elegance in the final result. So think again in Smalltalk. So elegance, analogy, multi-level approach, a uniform metaphor, these were the part of this methodology that Gaudí applied in this case, and in many others. You can repeat the analysis with other buildings. So this is, again, a method. So I will consider my theorem proved, at least for today. And I would like to finish with one reflection of all of these guys. I think these two are the same. And I'm pretty serious. Euclid rebuilt all the mathematics of his time from 5 axioms. You can say it wasn't he alone. There was a team around. Of course, yes. But the one that is always working is him. And Dan Ingalls did the same with computer science. He rebuilt all the knowledge we had before Smalltalk by following only 2 axioms, the object and the message sent. And we know that he succeeded. Okay? Well, that's all. Well, not sure that anybody has the next question. This is an inevitable joke. What's the next question? But if we are good here. Well, Dan Ingalls attended Smalltalks. Okay. And he's my personal hero. And he's the guy who really did the work and apply this methodology. So we all recognize all the work he did, and he is still doing. So I think it's a model to follow. Excellent question. Okay, let's relax. Thank you, guys.